Welcome to Metabolism and Bioenergetics Part 5. Here we'll actually look at the reaction energies that are underlying all of the energy production that we've talked about in this series of tutorials. Let's get started. Alrighty, so remember what we've learned about reactions, right? That we can think about them in terms of thermodynamics or kinetics. So far, what we know about thermodynamics is we've learned about delta H, which is the enthalpy, right? And we know that that is the energy difference, right, between the reactants and products. And so as soon as you hear about these, right, a couple reaction energy diagrams should come to mind, right? Energy along the y-axis, time along the x-axis, and so then we've learned that enthalpy, right, that when the products are lower in energy, we describe that as exothermic. We say that the enthalpy has a negative value. And then if the products are higher in energy, then we say that it is endothermic. And we show the enthalpy having a positive value. Okay, so these aren't complete diagrams, but just to kind of refresh our memory. And then, right, with kinetics, we should be thinking about the activation energy, right, and reaction rates. And so we're going to bring all of that together in this tutorial and connect it to the bioenergetics, right? So the main point here, looking at those same reaction energy diagrams, so nothing on the axis has changed. Just go ahead and fill that part in, right? And so the main point here is we learned that if we have a large activation energy, we have a slow reaction, right? So the activation energy is reactants to transition state. And so this would represent a slow reaction. And so then if we have, right, and if we have a small value here, we have a small hill to climb, we have a small activation energy, and that will characterize a fast reaction. Okay, so this page will be a brief review of things we've learned before. So these are two important concepts, right? And then remember that a catalyst is the substance that increases the rate of the chemical reaction without being consumed. So for example, up here, right, we would say that this reaction would be with the catalyst and this reaction would be without, right? And how does the catalyst increase the reaction rate, right? By lowering E sub A, right? Or you could think of it or as the transition state energy. Either way, right? Oops, let me slide that up, right? And then just to think back all the way to reaction basics, right? And collision theory, right? What is the activation energy? That is the minimum collision energy, right, that reactants must collide with for a reaction to occur. So the minimum collision energy of reactants, right, to reach the transition state. And of course the transition state, right, that's the particular arrangements of atoms in the reactants at their maximum energy level so that a reaction occur, right? So this is where we need to be for a reaction to occur. Okay, so what happens to reactant molecules that have less energy than the energy of the transition state? Nothing, right? No reaction. And and which biomolecules are catalysts? That's an easy one. Enzymes. Alrighty, okay. So we've pretty much, that's our review. We'll continue with a little bit more review, and then we'll start to introduce some new language and terms on the next page. So let's look at the next page. And so here's an opportunity for you to practice labeling reaction energy diagrams. So I'll go ahead and give you some time to do that. And then we'll compare answers, right? So we can see that reactions A and B are both exothermic because the products are lower in energy than the reactants. And we can see that reaction C is endothermic because the products are higher in energy. Okay, and then the transition state's been labeled for us here. We'll just go ahead and label there. Okay, and then this activation energy has also been labeled for us. We'll go ahead and label it here for the other two. Okay, and then if we look at the two exothermic reactions, it's very obvious that the smaller activation energy has the catalyst and the larger has no catalyst. Okay, now so that concludes the review. Now we're going to bring in some language that we haven't used before. So we have the idea of a spontaneous reaction. It continues on its own once started, versus a non-spontaneous reaction where energy must be continuously supplied for the reaction to continue. All right, so exothermic reactions, right? Once we've overcome the activation energy, right, they release additional energy to keep the reaction going. So exothermic reactions are described as spontaneous. Endothermic reactions, though, we're going to constantly need to be supplying energy because the products are higher than the reactants. So this is described as non-spontaneous. Oops, there we go. Okay, right? So, but why do we need to add energy to start an exothermic reaction, right? To overcome E sub A. Of course, once the reaction's going, then it fuels itself. Okay, so now that we've been introduced to the concepts of spontaneous and non-spontaneous, let's look at those a little more closely and expand our understanding of those terms to more about reaction energies. Alrighty, so so here's the definitions, and then here's a diagram. It's not the best diagram, it's a little dark, right? But here's somebody, right? For the rock to roll down the hill, right? We have to give it a little push, and then it will go by itself, right? So there's spontaneous, right? So we could think of that initial push, right, as the activation energy. Oops. Right, the initial push, think of that as the E sub A, but then as the energy is released, it's spontaneous. Now, if we want to push the rock up the hill, right, that is non-spontaneous. Right, this will require, right, it needs constant energy applied. Okay, so we've talked about it linguistically, and now we've had a diagram or a picture to help us really grab the essence of these words, spontaneous and non-spontaneous. So now let's think about them in terms of reactions. Okay, so the hydrolysis of ATP, we will learn that that is spontaneous. So we'll start using green. and that means that energy is released. So then the reverse process, to take ATP and bond it to phosphate, we would have to put energy in, non-spontaneous. Okay, so pretty much every reaction, most reactions are reversible, not every reaction, but in biochemistry they tend to be. And so just remember that if one direction's spontaneous, the other direction will be non-spontaneous. And then this gentleman by the name of Gibbs, he recognized that there was more to reactions than just the enthalpy. And so this developed the idea of Gibbs free energy, right? And so Gibbs free energy will take into account the enthalpies that we've already learned about. But then what Gibbs added was that we have to think about the temperature of the reaction and a concept known as entropy. And so, so we know a lot about enthalpy and we know about temperature. So to fully understand Gibbs free energy, we need to learn a little bit more about entropy. So let's take some time now to learn about entropy, and then we can finish looking at reaction energetics. Okay, so here we are. So entropy is a measure of the change in the degree of randomness or disorder in a reaction or physical change. All right, so it's sort of like electrons in this negative sense. It can be a little bit counterintuitive, right? So here we have less entropy or low entropy. The marbles are all stacked into a pyramid. And here we have more entropy, right? It's all random, more disorder, all right? So what's the spontaneous process, right? The spontaneous process is for the marbles to be in disorder, right? How do we get them into that pyramid? We are going to have to put energy in. That's definitely non-spontaneous. So this leads to a convention that is the opposite of enthalpy, right? When we gain entropy, right? So if we gain disorder, if we gain entropy, that is spontaneous, right? The tiniest little bump will create disorder, not very much energy, right? So when we lose entropy, right? Losing, right? So for gaining, right? You think of the plus, and losing, think of the minus. So to lose entropy, right? That is non-spontaneous. Imagine how long it would take to stack those marbles into a pyramid. Alrighty. Okay. Now, notice that this could actually be, in our definition, it could be a reaction or a physical change. So let's think about that for a minute. All right, so when products are more disordered than the reactants, right, then we have gained entropy. So we would say plus delta S, and we recognize that is going to be spontaneous. When the products are less disordered, then we lose entropy, so we give that a minus sign, and that's our non-spontaneous. Okay, so let's, so that would be for a reaction. What about changes of state, right? So if we think about the kinetic theory of matter and what we've learned about the various states of matter, right? Who has the most entropy? It's definitely going to be gas, right? They're completely independent of each other, dominated by kinetic energy. Liquids have more entropy and disorder than a solid. So as we move from a solid to a liquid, we gain entropy, and from a liquid to a gas, right? So these are plus delta S. These would be spontaneous. The reverse, right, to go from a gas to a liquid or from a liquid to a solid, in this case, we're losing entropy. So these would be the non-spontaneous phase changes, right? And we know a little bit about that. Okay, we can also look a little more carefully at the complexity or the number of reactants versus products, right? So as the complexity or the number of products increases, then the entropy increases. And so we would say that that is a plus delta S and spontaneous. Okay, and so then obviously the reverse would go the other way. Okay, so there we have the concepts, but let's apply them, and let's practice applying them, right? So we have the knowledge, let's build the wisdom. Alrighty, so if we look here at this first reaction, we're going from a ring to a straight chain, right? So think about, we know about the structure of organic molecules, right? Which one has more disorder? Think about all of the different conformations that the straight chain can go into that are not possible because the ring is closed, right? So we would say that there's more order in a ring and less order in a chain. So this would be an example where we increased our entropy, and so we would describe it as spontaneous. Now let's look here at, right, we have water as a liquid going to water as a solid. So here we would have less order, right? Definitely more order, right? If we spill a glass of water, it makes a big mess. Drop a couple ice cubes, not a big deal, right? So we've lost entropy, non-spontaneous. Alrighty, and then this last example here, let's look and see. So, what do we judge by? Well, if we look here, we see we have 6 moles of reactants, but we have 7 moles of products. So we've definitely increased the entropy. So if you've ever had to babysit or taken care of children or animals, you know that it's a lot more energy to take care of 7 than 6. Okay, alrighty. So now we've reviewed enthalpy and reaction energetics, and we've been introduced to the idea of spontaneous and non-spontaneous and entropy. So now we finally have everything we need to put this all together. So we can look at free energy in all its facets. So let's remember the formula. The Gibbs free energy is the enthalpy minus T delta S. Now it's important here to keep in mind that this negative sign is part of the formula. All right? So when we think about the Gibbs free energy, you can think about this as the overall, right, the overall reaction energy, allowing for all the different aspects. Okay, so this leads to a bit more of language to learn. It builds off what we've learned about enthalpies, right? So when you hear exergonic, right, so it's very similar to exothermic, right? It's the release of free energy. So this will be very analogous to what we learned about enthalpies, right? If we're releasing energy, we say that that is spontaneous, right? And the value of delta G would be negative, right? And the other way to show a negative value for delta G is to show that it's less than 0. And so then, quite logically, here we have endergonic, so that requires the input of energy, So that'll definitely be the non-spontaneous pathway. And so since we have to put energy in, we put the plus, or we could describe it as delta G is greater than 0. Alrighty, so these reaction energy diagrams look very familiar. We've seen them before, but now they're more all-encompassing. They're taking into account entropy, enthalpy, and reaction temperature. So we look here and we see that the products are lower in overall energy than the reactants. So this would be a negative delta G, and we would describe it as exergonic. And over here, we see that the products are higher in overall energy. So that would be a positive delta G, endergonic. Okay, and we've already written the value, the relative value, positive or negative on the charts. So that's all taken care of. Okay, so now let's, before we go to the next page though, I want to do a little exercise with you to help warm you up for the next concept. Alrighty, so let's say that we have a very large positive number. It doesn't matter what it is. And let's say we have a very small negative number. All right? What happens when we add those two numbers together? Are we going to get a positive number or a negative number? Right? Well, if we have a very large positive number, we know that our final result will be a positive value. Right? Likewise, let's say we have a very small positive number, and we have a very large negative number. What happens when we add those together? We know that we'll end up with a negative number. Okay? So this very simple concept is what we're going to use on the next page to make some predictions about Gibbs free energy. So let's go ahead and move to the next page. Alrighty, there we go. And so now we can look. There really are not that many possibilities here for the Gibbs free energy, right? What do we know? We know that the enthalpy has to be either positive or negative, right? So if we look here, endothermic, exo, endo, exo, and we know that we can either lose or gain entropy. And then something that I haven't brought up before, but I'll bring it up now, the temperature is in Kelvin. So when the temperature is in Kelvin, what do we know about the values, right? They're always going to be positive. Okay, so now let's think about, right, if we have a positive value for the enthalpy, and then there's a negative in our sign, and we have a loss of entropy, right? So a negative times a negative makes a positive, right? So our enthalpy term is going to be positive. And then the negatives, if we take the negative sign of the formula and the negative sign of the entropy, then we know we're going to end up with a positive. So we know that the overall energy is going to be a positive delta G. And so it doesn't matter what temperature we use, this is going to be a non-spontaneous process, and we will always have to add energy to make it occur. Now we'll look at the next scenario. For the next scenario, we'll see that, okay, we have a negative, so it's exothermic. We describe that as spontaneous. And then we have a negative sign, right, and then a plus. So if we multiply those out, we see that we get two negative values that we're going to add together. So the overall Gibbs free energy will always be negative. The temperature doesn't matter because we're adding two negative numbers, and temperature is always positive. So this will always be spontaneous. Okay, now let's get to a different scenario. All right, so here we have endothermic. We have a positive delta H, and then we have the minus sign of our formula, and we're going to have temperature, and I'm just going to go ahead and there's the minus sign and the plus, so we'll just put a negative in front of temperature. Okay, so just with magnitude, we see that we're going to have a positive value added to a negative value that's going to depend on temperature, right? So we don't know, if we have a positive and a negative term, we don't know who's going to win because it depends on the temperature. And so which is going to favor, right? So a spontaneous reaction is a negative delta G. So we can see here that the higher the temperature, the more likely the combined result will be negative. So we would say that high temp favors spontaneity. All right. And then let's look at the next example. In the next example, we have our enthalpy is negative, and then we have a minus sign, right? We're losing entropy, and we have a minus sign in our formula, so that becomes a plus, and then we have the temperature. So we can see here that temperature is always positive, so we have a negative value and a positive value. So once again, the net result is going to depend on the temperature. And here we see, right, we want to have a negative delta G. So here we see a low temperature favors spontaneity. Right, because remember, a negative delta G is spontaneous. Okay, so let's check for some understanding here. Is an exothermic reaction or process always spontaneous? Right? No. Right, let's look. Here are our two exothermics. Right, we have exothermic here and exothermic here, right? Because we have the negative delta H. So notice, right? So in one case it is spontaneous, but in the other case, no, right? We'd have to have low temperature, right? So explaining this, right? So no, right? Because the spontaneity, right, is determined by more than just the enthalpy, right? It also depends on, right, temperature and delta S. Okay, so that's why learning enthalpy wasn't enough. Okay. So now we can see that the actual 7.3 kcals is actually the overall free energy. It does incorporate the entropy and the temperature. And so if we look here, right, we recognize, right, that the hydrolysis is a spontaneous process. So we would add the free energy, right, the negative sign, right, that negative sign tells us exergonic. So think of the kcals as a product. And so then if we show the reverse reaction, then of course we would put the 7.3 kcals as a reactant, right? And then here it would be endergonic, right? So it's just another way to show the forward and reverse reactions. And now for the grand finale here, this last page, we'll put this all together to see how it links with biochemical reactions. So what we see is within our biochemistry, what we do is we couple reactions. So especially for anabolism, right? If we want to build larger and larger molecules, we're going to need energy. And we say that energy comes from ATP, but let's look at exactly how that happens. And we'll also just look at it in terms of transferases as well. Alrighty. Okay. So here we'll look at the first step of glycolysis. And we see that we have glucose forming glucose 6-phosphate. So we'll abbreviate glucose with a G. And then there's our glucose 6-phosphate. And so we have to bond it with a phosphate molecule, or ion. And we produce water. And notice that this is endergonic. It needs 14 kilojoules of energy. And then ATP, so just a little switch of energy units just to kind of keep our brains flexible, right? But we know that ATP hydrolysis is exergonic. So this is how we couple reactions, right? So these aren't in sequence, they're coupled together, happening simultaneously. So we can treat this like a simple algebraic expression where we have two different equations. And so we're going to add them together, right, because they're coupled. So we look on the reactant side and the product side, and we look for common terms, right? So we notice here, we see that, oh, there's a phosphate on the left and a phosphate on the right, so we can cancel those. And we see there's a water on the left and a water on the right, so we can cancel those. So the net reaction then is we have glucose reacting with ATP to produce glucose 6-phosphate, ADP, and 1 hydrogen ion. So then we look at the overall energy of the process. So we have 14 kilojoules that's endothermic or endergonic, and minus 31. So when we do the math, we see we get minus 17 kilojoules per mole. So the coupled reaction, so by coupling the two reactions, the coupled process, right, is exergonic, right, and spontaneous. So here's an example of how ATP fuels reactions within our body. So now we'll go ahead, and here's one for you to try. So this is a good time to pause the video if you want to give it a go, and then we can compare answers. Alrighty. So here we have an example of fructose 6-phosphate, and it is going to gain a phosphate group. Notice the change here. We see that the phosphate's getting transferred, right, and it's coming from ATP to ADP. So once again, we have an endergonic reaction coupled with the exergonic hydrolysis of ATP. So we'll go in once again and look for common factors. So we see the phosphates and the waters are the common factors. So the fructose 6-phosphate reacts with ATP to produce the fructose 1,6-bis phosphate, right, ADP, and a proton. And so then the net result here is minus 15, right? So once again, by coupling the two reactions, we created something that's exergonic, right, and spontaneous. Okay, so let's see. And then just to kind of keep in mind, just a little footnote. So remember that exergonic reactions are described as being spontaneous, but they don't tell us how quickly they occur, right? We still need those enzymes to reduce the activation energy. Alrighty. So this wraps up our close look at Gibbs free energy and its underlying role in bioenergetics. Please take some time now to work a few homework problems to reinforce your understanding.